Hey everyone, and welcome to this explainer. Look, we're skipping the usual long intro today because we are jumping straight into a high-stakes troubleshooting session. If you're gearing up for the Cambridge IGCSE computer science exam, I know you already have the basics down. So today, we're going to crack the code on those specific, sneaky little mistakes that quietly cost students top grades. We're going to break down the core concepts of memory, binary, and architecture, but exactly the way the examiners want to see them. Let's get right into it.
Okay, check out this quote. The computer uses RAM to load the startup routines because it is fast. I mean, it sounds totally believable, right? It makes perfect logical sense at first glance. But here's the reality. This is a classic cold open mistake. 9 out of 10 students will write something almost exactly like this in an exam, and they will instantly lose marks. Let me show you exactly why this happens so you don't fall into the same trap.
So here is why that answer completely fails. It all comes down to the fundamental difference in how these two types of memory actually function. RAM, or random access memory, is just the temporary working area of your computer. Crucially, it's volatile. That means the second the power gets cut, boom, all that data vanishes. On the flip side, ROM, or read-only memory, is non-volatile. That data is locked in. It stays permanently stored even without power. Think about it. If a computer stored its essential startup routines in RAM, it would literally forget how to turn on the moment you unplugged it.
All right, so let's walk through what the actual correct startup sequence looks like. When you hit that power button, your computer doesn't just guess what to do. The BIOS, the basic input-output system, takes over. This BIOS is firmware, and it's permanently stored on a flash memory chip called an EEPROM. The BIOS is essentially the middleman here. Its main job is to tell the CPU exactly where the operating system is hiding on the storage drive. Only after it does that is part of the operating system loaded into the temporary RAM, so you can actually use your computer.
Now, knowing these facts is one thing, but writing them down in a way that gets you full credit? That's a totally different ballgame. Here is the ultimate exam upgrade for you. Generic answers, like just listing off component names without any real context, are super weak. They bleed marks. High-level answers, they are scenario-anchored. This means if the exam question gives you a specific real-world scenario, you absolutely must use those scenario nouns in your response. You explain the technical mechanism, sure, but then you anchor it right back to why it matters for that exact situation.
And speaking of securing marks, let's pivot to our next major trap, mathematics, specifically binary addition. There are 4 golden rules you have to know. 0 plus 0 is 0. 0 plus 1 is 1. But look really closely at the third rule here. 1 plus 1 is 0, carry the 1. Why? Because the number 2 simply doesn't exist in binary, so the value becomes 1, 0. And if you have to add 3 ones together, the value becomes 1, 1, so you write 1 and carry 1 to the next column. Honestly, mastering this carry bit is absolutely crucial.
Which brings me to a massive, literal examiner red pen warning. Guys, when you see command words like calculate or show, you must always show your working bits. Examiners require you to show those tiny carry bits in your binary addition to give you full marks. And here's the crazy part. That applies even if your final binary answer at the bottom of the page is completely wrong. If you make a silly addition error but your workings prove you understood the process, you can still salvage marks. So never ever do the math purely in your head.
Now what's really awesome is how we can take another huge headache, converting binary to hexadecimal, and make it super simple. Memorizing long strings of bits is just a nightmare. So instead, we use the nibble method. Check this out. You just take your 8-bit binary number, your full byte, and slice it right down the middle into 2 4-bit nibbles. Since every single hexadecimal digit perfectly corresponds to exactly 1 4-bit binary nibble, this conversion becomes entirely foolproof. You just calculate the 2 halves completely independently and then push them right back together. Bam, done.
Let's shift gears for a second and talk about programming logic. We're going to use a really fun, real-world analogy to nail down the difference between integer division, which is div, and modulus, which is mod. Imagine you've got 230 students and a fleet of school buses that hold exactly 52 seats each. Integer division, div, only gives you the whole number. So 230 div 52 equals 4. It tells the programmer exactly how many buses are completely 100% full. Modulus, or mod, only gives you the remainder. So 230 mod 52 equals 22. It tells you there are 22 students left standing on the sidewalk who still need a ride.
Real quick, let's pause for a massive concept distinction because I see students fall into this trap constantly. Do not mix up validation and verification. Validation is when the computer checks if the data you entered is reasonable, sensible, and actually follows the rules, like making sure someone didn't type in that they are 900 years old. Verification is an entirely different beast. It's checking if the data entered exactly matches the original source, usually just to catch typos during data entry. They are two totally distinct concepts, so make sure you keep them separated in your head.
Jumping back over to hardware, let's talk about CPU core functions and what I like to call the vagueness trap. When an exam asks you about computer architecture, just dropping names like the arithmetic and logic unit or the control unit, not going to cut it. You have to explain the mechanism and the consequence. You need to explicitly state that the ALU carries out the arithmetic and logic operations, and that the control unit generates the signals to synchronize data flow and program instructions. Remember, precision beats short labels every single time.
And to guarantee you're hitting that level of precision, I highly recommend using this 4-step mastery path, especially for explaining data transfer in buses. Just walk yourself through these structured prompts. First, what is it? Define the specific method. Second, how does it work? Explain the technical sequence. Third, where is it used? Apply it to the given scenario. And finally, why use it? Justify why it's better than the alternatives. Run your answers through that quick 4-prompt check, and your explanations will be totally bulletproof against vague wording.
Okay, let's actually put this to the test. 10-second challenge for you. Imagine a question asks you to describe packet switching for a hospital's network. You write down a totally flawless textbook definition. You're talking about headers, payloads, routing, the whole 9 yards. But wait, what's the error? The error is that you didn't mention patient data or medical records or the hospital system even once. You used floating abstractions. You completely forgot to anchor all that great technical vocabulary to the actual real-world scenario they gave you.
So how do we fix that? By shaping a highly disciplined exam response. Take a look at this structure. True mastery means getting your logic in the perfect order. You transition from just understanding the concept, you layer in the precise technical vocabulary, and then you build a tight logical sequence. You explain the internal mechanism first, and then directly state the consequence, but tailored perfectly to the scenario. It's not just about what facts you know, it's about exactly how you format what you know.
All right, as we wrap this up, before you sit down for any paper, you have to drill this checklist into your brain. These are your absolute non-negotiables for success. Number 1, have you used the specific scenario nouns from the prompt? Number 2, have you visibly shown all your mathematical workings, especially those little carry bits? And number 3, have you checked your data types and limits to avoid things like overflow errors? Keep this mental checklist handy. And hey, if this explainer made these concepts finally click for you, make sure to subscribe to the YouTube channel Ace the Exams at acetheexams_IGCE for more deep dives.
I want to leave you with this final thought. Just memorizing textbook vocabulary, it's simply not enough anymore. The real test, the thing that actually gets you top marks, is can you confidently apply that underlying mechanism to a completely new, real-world scenario? Challenge yourself. Don't just know the terms. Understand how and why they actually work in the real world. Keep practicing, stay curious, and I'll see you in the next explainer.